In this lesson, we are going to continue with the revision of Science Paper 2 for 2021 GCE. Now here, we have a question 5. Fluorine gas is bubbled through a solution of potassium bromide as shown in the diagram below. So this diagram is giving us a picture of how fluorine gas was bubbled through a solution of potassium bromide. Now, the first question here is describe what would be observed in the test tube. So, want to see what happened after fluorine gas was bubbled through this potassium bromide. So, for us to come up with the point that we can give in terms of what happened, first we need to look at was there a reaction when fluorine was bubbled through? So we have to check if the reaction was there. So first let's look at group 7 elements. So the first element for group 7, we have the fluorine is on top. Then we have chlorine. We also have the bromide. Then we have iodine and so on. So now we can now go back. We can now go back to the reactivity series of group 7. So group 7 will say as you move up the group, the reactivity series increases. So what it means is the element above is more reactive than the element below. So bromine is more reactive than iodine. Chlorine is more reactive than bromine and iodine. Then fluorine is more reactive than the 3. Why? Because it is on top. So therefore, we can see that since the reaction was potassium bromide, potassium bromide plus fluorine. Now, since fluorine is more reactive than bromine, the fluorine will displace the bromine, giving us potassium fluoride plus bromine solution. So since now the reaction took place, so we want to look at now what happened in terms of what was observed. So what will be observed is we are expecting to see the color of bromine in the solution. So we can see that the color changed. The color changed to reddish brown. So this is the color of, or sometimes we can say bubbles were seen. So we are expecting to have the change in terms of color. Then the second one also, sometimes you may have bubbles, unless it is at room temperature where we are expecting our bromine to be in a liquid state. Now let's look at Roman number 2. Write a balanced chemical equation for the reaction that occurs in the test tube. So the reaction is this that I've written. So here we are saying we have potassium. So potassium, the reactant potassium bromide and fluorine. So plus fluorine. Then we have the product potassium fluoride plus bromine. Okay, so we can see that the fluorine displaced the bromine. So therefore, this is what we call a single displacement, because one element was displaced. So the one that is being displaced is less reactive. Then the one that does the displacing is more reactive. So we can now put into chemical symbols. So the chemical formula for potassium is K, bromine Br. These two have the valences 1 to 1. then aqueous plus. Now fluorine, here fluorine will have a diatomic, then we are going to have a potassium fluoride, aqueous plus bromine will have a 2 since it's on its own. So we can now see we want to balance. So here we can see that on the product side we have 2 atoms of bromine, but on the reactant one, so we can put a 2 in front of potassium bromide. So we can see that we have 2 potassium and also 2 bromine. So we can see that even here we need to have a 2, so that we can see that we have 2 potassium and 2 fluorine. So therefore our equation is now balanced. Okay, now we can move on to question B. What would be observed in the test tube if iodine was bubbled through the potassium bromide solution? Give a reason for your answer. So now here we have a question where we are asked to give what we think would happen if iodine was used instead of fluorine. So let's see first if the reaction can take place. So we still have our potassium. We still have our potassium bromide plus iodine. So we have to check if the iodine has the ability to displace bromide. So let's look at the position of iodine. So bromide is here. This is where our bromide is. Then this is where our iodine is. So from the way the arrangement are arranged in group 7, we are able to see that bromine is more reactive than iodine, since bromine is on top. So therefore iodine cannot displace bromine. So we are expecting to have the same product. So we are going to have bromide plus iodine. This time no reaction will occur, since iodine is less reactive. So the observation is nothing will change. The reason is the iodine cannot displace bromine, since it is less reactive than bromine. So we can say observation, nothing will change. Nothing will change. In brackets we can say no reaction. No reaction will occur. Okay, now for the reason we are saying iodine cannot displace bromine. So iodine is less reactive than bromine, and it cannot displace iodine. So this is what would happen. So whenever you have reactions like this and you are given a question where you need to give the reason of what you think happened, first you need to ask yourself, is the reaction going to take place? Then from there you can drive your conclusion from there. Okay, so now we can move on to question 6. Question 6a, define the rate of chemical reaction. Now let's say we have a beaker. This is our beaker. Then let's have a picture that we have some particles inside this beaker. Okay, now when a reaction is taking place, these particles must collide with each other. So if we have a particle, this is a particle, or we can just say we have an atom, then another atom. So if this atom A collide with atom B, we can now say the reaction is taking place. So the reaction, whenever we have a chemical reaction, we are just looking at the collision, how particles collide in order to produce a product. Now the rate of a chemical reaction tells us how fast the particles are colliding with each other. So if the particles are colliding slowly with each other, we can say the rate of a chemical reaction is slow. In a case where we have the rate of chemical reaction fast, that simply denotes that the speed at which the collision is taking place is fast. So therefore, the rate of a chemical reaction tells us the speed at which a reaction proceeds. So we can say the speeds at which a chemical reaction proceeds. So this is how we can simplify the definition for a rate of chemical reaction, or we can also say the change in concentration the change in concentration of reactants over change in time. So what this means is when a reaction is taking place, the concentration of reactants reduces. So now the speed at which the concentration is reducing and how much of time is taken for that concentration to reduce also simply means the rate of a chemical reaction. Okay, let's move on to question B. State a reason for each observation below. Roman number 1, hydrogen peroxide decomposes much faster in the presence of the enzyme catalyst. So here we are looking at the factors that affects the speed of a chemical reaction. So why is it that when a reaction has a catalyst, it proceeds faster compared with a reaction that has no catalyst? So therefore, like I said earlier, for these two particles to collide, there is a certain amount of energy that they should possess, and this energy is known as activation energy. So until they reach this activation energy, will the reaction start to take place. So what it means is if this activation energy is not achieved, the reaction cannot take place. So what the catalyst does, it only reduces the activation energy. So that is how a catalyst speeds up the chemical reaction. So by reducing the activation energy needed for the reaction to take place. So we can say an enzyme catalyst will help to speed up the rate of a chemical reaction by reducing activation energy. So this is what the catalyst does. So it only reduces the amount of energy needed for a reaction to start taking place. Okay, now let's move on to question 2. So here the reaction between manganese carbonate and dilute hydrochloric acid speeds up when some concentrated hydrochloric acid is used. So here we are looking at concentration. So we want to look at how does concentration makes the reaction to be faster. So how is the increase in concentration increases the speed of reaction. So let's have a picture. We said that for a reaction to be fast, for a reaction to take place, the particles must collide. So let's have two beakers. Let's say here we have these particles. Then we have another beaker, the same size beaker, but here let's say we have maybe 4 particles. So we can say we have beaker A and beaker B. So if these two reactions in each beaker starts to take place, we can see that in beaker A, the particles are in higher concentration. So here there is a higher concentration, then here there is a lower concentration. So where there is a higher concentration, we can see that the particles are closer to each, and it is very easy to bump each other when the concentration is high, compared here in B, where the particles are far away from each other. So for a particle to move and reach the other particle, it takes time and also a certain distance. So where there is a higher concentration, it means the particles are closer together and they are able to collide with each other easily. So that is how a higher concentration makes the reaction faster. So you can just have a picture where, let's say you are in a crowd of people where there is a lot of people. It is very easy for you to bump into someone compared where there is less of people. So that is also what happens whenever we are dealing with a reaction. So here we can say the higher concentration makes the particles to be closer to each other, and be able to collide easily. So that is what the concentration does. There is a high chance of a particle colliding with another particle since they are close to each other. Okay, now let's look at the other question, the last one. So for the last one, we are looking at the powdered magnesium is used in fireworks rather than magnesium ribbon. So here we are looking at the size of the particle. So how does the size of the particle affect the speed of a reaction? So let's have a picture again. Here we have a particle with this size, then another particle with this size. Then we have this particle and also this particle. We are saying for these particles to react, they have to collide, and also for these to react, they have to collide. So where we have big particles, we can see that it is not easy for a big particle to move toward the other particle, but for a small particle, this small particle, it is very easy to move and bump into this because it is lighter. So therefore the size, we are saying if we decrease the size of the reacting particles, we are increasing the speed of the reaction, because the smaller the size, the higher the speed of the reaction, and the increase in the speed of the reaction is coming as a result of the smaller particles are easy to move compared to big particles. So we can say the smaller particles does not require a higher kinetic energy to move toward each other. So this is what the smaller particles does. So it is very easy for a small particle to move, and the amount of energy that will be used by a smaller particle will differ from the one that can be used by a large particle will require a large amount of energy for this particle to move toward the other particle. So these are the answers for question 6. Okay, so now we can move on to question 7. During the extraction of zinc, the ore is first roasted in air as illustrated by the equation below. So we have zinc sulfide plus oxygen will give us zinc oxide plus sulfur dioxide. Now the first question, give the common name of the ore in the above equation. So this zinc sulfide is the chemical name, so the name that they use under chemistry. Now we want to look at the common name for zinc sulfide. So this is a zinc blend. Okay, so now let's move on to question B. Name the substance which can be used to reduce zinc oxide. So if we want to reduce, we are looking at, we have a zinc oxide. So we want to know the substance that we can use to remove oxygen so that we may have the zinc now alone. So the substance that can be used to remove the zinc, to reduce the zinc oxide to zinc is carbon. Carbon, which is also known as a coke. So carbon can be used to reduce zinc oxide to zinc. C, suggest a reason why sulfur dioxide should not be allowed to escape into the atmosphere. So the negative impact of sulfur dioxide, when it dissolves in the atmospheric water vapor, it produces acidic rain. Then the acidic rain later will destroy the plants, and also it may collide the other living organisms like animals. So we can say when it dissolves in atmospheric water vapor, okay. It produces acidic rain. So that is the negative impact of sulfur dioxide if allowed to go into the atmosphere. So it produces the acidic rain. Then the acidic rain may corrode the living organisms such as plants. Now here we have state one use of zinc. So zinc, it can be used to make alloys such as brass and bronze, and also zinc can also be used for galvanizing. We are saying if we want to protect one metal from getting rust, so we can use zinc to galvanize a sensitive metal in terms of rusting. Okay, now we can move on to question 8. The structure displayed below is a polymer that was formed from monomer Y. So here we have a polymer. Now a polymer is a large molecule made from small units known as monomer. So what we are saying is, under organic chemistry, there is a monomer. So a monomer is just a smaller unit. So if we have two monomers, or maybe more than two monomers, if we combine two or more monomers, we form what we call a polymer. So this is where the concept for this question is coming from. So we are dealing with a polymer. So a polymer is made from the monomer. Now, the other thing that you need to know is monomers. The monomers must be the alkenes. So, and alkenes, we are saying there should be at least one double bond between two carbons. So now, apart from knowing that there should be, the monomer should be the alkenes, also we have to know that always a polymer must have the single bonds. As we can see from the structure given here, we are able to see that we only have single bonds between carbon atoms. Okay, then from there, the first question, our question A, is name the polymer. So we are trying to name this polymer. Now, for you to name the polymer, the first step that you are going to do is we are going to identify the monomers that were used for them to come up with this polymer. So how are we going to come up with this? So we are going to divide this structure into two. So we need to divide this structure into two. So this is how you do if you are trying to find the... Okay, then let's compare the two structures. From the two structures, we are able to see the way the atoms of carbon and hydrogen are arranged. So here we can see that we have CH3 down here, even CH3 up there. Also, we can see that even the other one, we have the exact copy. So that is how you can identify the type of the monomer that was used. Now, let's now try to draw this monomer in a general way. So what we are going to do is, let's say we are going to draw it like this. This carbon, let me just write it the way it is. So I've gotten one of the monomer from there. Then we are going to make the actual monomer the way it was before the chemical reaction. So we can see that we have 4 carbon atoms. So we have carbon 1, 2, 3, and 4. So we are dealing with a 4 carbon atom monomer. Then from there, we need to know that the way the monomer was before a chemical reaction, like I said earlier, we said there should be a double bond between 2 carbons. So the double bond was on this position. Then here we have the other carbon. Also here we have this carbon. So we can see that the 3 hydrogens for each carbon, like the carbon number 1, these are the 3 hydrogen. Then for this one, it also has 3 hydrogen atoms. Then for this one, we can put hydrogen, and also we can see that. So this is how the structure of the monomer was before a chemical reaction. So we can see that each carbon is surrounded by 4 bonds. So the carbon must have the 4 bonds. That is the way it should be written. Then from there, now for us to name the monomer, we are going first to use what we call the prefix. So say meth has 1 carbon, like methane. Eth has 2 carbons. Prop 3 carbons. Bute 4 carbons. Pent 5 carbons. Hex 6 carbons. So we'll just end there, because the one we are looking for is the one with 4 carbons. So we are looking for a but. So you say now but. Now after you write the prefix, mind you, this is what we call a prefix. A prefix determines the number of carbons a molecule has. So but now we need to have this double bond. So whenever you see the double bond, the suffix is always ene, because these are known as the alkenes. So we have the alkenes. So the ene indicates an alkenes, or presence of the double bond. Now, away from there, we also have to look at the position where the double bond is located. So let's count this one as our carbon number 1. Here, carbon number 2. This is carbon number 3. Carbon number 4. Okay, let's also number it from this side. So say carbon 1, 2, 3, 4. So now let's check where the carbon is located. So we can see that if we start from here going this side, we can see that the double bond is on carbon number 2. If we start from this side going this direction, we can see that the double bond is on the carbon 2. So here we are having the same number. But if you have a situation where you have maybe The other direction has carbon, the bond is found on carbon number 2, then the other one has a bond on carbon number 3. You always go with the lowest number. But in our case, where regardless of the direction that we take, we are able to see that the double bond is on carbon number 2. So we are going to pick our 2 like this. So this is the name of the monomer that was used. Now, in order to come up with the name of the monomer, polymer, you just add the word poly. So our name will be poly. So this is what we were looking for. Then B1, name the monomer Y. We've done the monomer Y is okay. From there, construct the displayed structure of monomer Y. We've constructed. So we just say C or if we want, we can write it like this. Okay, so then we have another question here. Monomer Y was reacted with steam under a suitable condition and an organic compound Z was formed. So the monomer Y here, the key is it is an alkene. So here we are looking at what happens when an alkene is reacted with the water. So remember, there is a property of an alkene where if an alkene reacts with water, it forms an alcohol. So alcohol is produced and the process is known as hydration. So hydration is just the addition of water to an alkene in order to form an alcohol. So after the steam was added to monomer Y, an alcohol was formed. So Roman number 1, to which homologous series does compound Z belong? So the Z, we are saying, was formed after the addition of water. So this should be alcohol or alkanose. Okay, then from there we have the last question. Write the general formula of the homologous series stated in C1. So these are alcohols, so they have the formula of CN, 2N plus 1 OH. So these are the answers for this video. Thanks for watching and don't forget to share and also subscribe to the channel.